To my fellow concerned citizens, if we are ever going to stop geoengineering, we need to know as much about it as possible. For those of you who do not know what geoengineering is, it looks like what you're seeing on your screen right now. This is David Keith of the University of Calgary. David Keith is probably the most prominent person in the geoengineering arena. He has testified before the United States Congress on the issue of geoengineering and advises them as to the technical aspects. Let's watch a 1-minute video clip of what this man has to say.
There's no question that large-scale climate engineering is untested and dangerous. We've mostly thought about sulfur, and there's a lot of good reasons to think about sulfur because sulfur is what nature does, and there are very good reasons to think we would like to start very slowly if we ever wanted to do this and do something that was an analog to nature because we have some idea what the downsides of what nature does are. Nevertheless, there might be some good reasons to think about alumina. The big deal really is that alumina has 4 times the volumetric radiative forcing for small particles as does sulfur. And that means you have 4 times less surface area for the same radiative forcing. And this is a much bigger deal. You have roughly 16 times less the coagulation rate. And that's the thing that really drives removal. So you could get away, we think, with much smaller mass fluxes. But we haven't run those studies yet, so that might be wrong. The little picture is from a nanofabrication study, which shows you can make very high quality, and do this in just a jet in a very simple way, make high quality alumina particles just by spraying alumina vapor out. Certainly in principle possible to do that. There's a big literature that's already looked at.
So what is David Keith trying to say? He is saying that he and his fellow geoengineers have given up on the idea of spraying sulfur from aircraft and now prefers the idea of spraying alumina. Why? Because according to him, alumina will reflect 4 times as much light back into space and has 16 times less coagulation than sulfur. In other words, the alumina particles do not clump together in big pieces and fall down quickly. So in essence, if you take the 4 and the 16 and multiply them, he's saying that alumina is 64 times better than using sulfur. He is also saying that you can spray aluminum out of aircraft and create high quality alumina particles. However, there is another reason why geoengineers do not want to use sulfur. They will not tell you this, but sulfur is yellow and would leave extremely obvious trails behind the aircraft. Also, sulfur has an extremely bad smell, which many people call the rotten egg smell. While trying to conceal geoengineering, geoengineers know that they cannot have yellow streaks in the sky and strong odors falling to Earth. There are some people who spend their time on the internet trying to convince other people that chemtrails are not real. These people say that what people are witnessing is just persistent contrails. These people point to photos such as this one and claim that because there is a gap between the engine and the beginning of the trail, that chemtrails are just contrails. They say if something was being sprayed, it would be evident right from the very beginning of the engine. The rest of this video will explain the reasons why even aircraft that are spraying chemtrails would have a gap between the engine and the beginning of the trail. It is time to share with you how I think chemtrails are being accomplished. Trimethyl aluminum. The first thing I want to talk about is its molecular formula. It has 6 carbon atoms, 18 hydrogen atoms, and 2 aluminum atoms. Gasoline can vary between C6H14 and C12H26, and it averages somewhere around C8H18. Trimethyl aluminum is a combination of hydrocarbons that closely resembles gasoline, and aluminum. Jet fuel is basically kerosene, which is also a hydrocarbon. The next thing to notice about trimethyl aluminum is its appearance. It says colorless liquid. Gasoline is colorless. Look in a jug of gasoline and you'll see that you can see clear to the bottom. Just because there's a little bit of aluminum does not mean that it's going to have color. Let's talk about what trimethyl aluminum does when it hits air. Wikipedia has this to say about trimethyl aluminum. It evolves white smoke as aluminum oxides when the vapor is released into the air. Wikipedia also says that trimethyl aluminum is used in what is called sounding rockets, which are used to study the upper atmosphere wind patterns. The trimethyl aluminum is used to create a tracer, a smoke trail, white smoke, to study the wind patterns. Geoengineer David Keith talks about having to spray up to 20 million metric tons of aluminum per year. Because a metric ton is just 1/3 of a pound short of 2,205 pounds, 20 million metric tons is a little bit over 44 billion 92 million pounds per year. David Keith and the University of Calgary contracted Aurora Flight Sciences to do a cost analysis of what it would cost to do geoengineering. In that report, they determined that 747s would be the best way to do it. Probably because 747s already transport half the world's cargo, thus making it not necessary to build new aircraft. In the 1-minute video clip, David Keith spoke about spraying aluminum vapor out of aircraft to make high-quality alumina particles. That makes sense because alumina is aluminum oxide, which is very hard and would destroy engines. On the Mohs hardness scale, alumina rates 9 to 9.5. However, aluminum only rates 2.75. The melting point of aluminum is 660 degrees Celsius. The combustion chamber in a jet engine is between 1800 and 2000 degrees Celsius. So, the aluminum would melt and create a nice vapor. In the combustion chamber, the air and the fuel is being mixed in the proper ratio, and because the combustion is about 99% efficient, there is no air or oxygen in the combustion chamber to react with the aluminum and change it into aluminum oxide and therefore make it visible. This air pressure calculator shows, at the ceiling height of 45,000 feet, which is the highest a 747 can go, the barometric pressure is so low that there is only 16% of the oxygen which is available at sea level. More typical 35,000 feet, there is only 26% of the oxygen which is available at sea level. The aluminum is flowing into a very low oxygen environment and therefore would take time to turn to alumina and become visible. But there's one more aspect to look at. According to Boeing, the forward engine nozzle is at 128 feet from the tail, and the rear engine nozzle is at 97 feet. This is a study done by Boeing. This was done under conditions of zero wind. The study was done on the ground, and they prevented the airplane from moving. With the engine nozzles 97 to 128 feet in front of the tail, and the chart showing that the wake is at least 240 feet behind the tail, the total wake is at least 337 to 368 feet. Obviously, a jet engine leaves a large wake. When the aircraft is moving, the wake will not be as long. Aluminum requires oxygen in order to turn into alumina, or aluminum oxide. There is virtually no oxygen in the combustion chamber. Then the aluminum vapor exits out the engine into air that has very low oxygen content at altitude, and the massive thrust from the engines creates a very large wake that is devoid of oxygen. So the real point is this. The aluminum vapor coming out of the engines has to go back far enough to seek out oxygen before it can turn into alumina, turn white, and become visible. And that is why there is a gap even with aircraft that are spraying chemtrails. Regardless if they are adding aluminum or trimethyl aluminum to the hydrocarbon fuel, during takeoffs and landings, how do you make sure that you do not spray chemtrails? Let's take a look at a 747. Filled to maximum fuel capacity of 57,285 US gallons, the maximum range is 7,260 nautical miles. 7,260 nautical miles is 8,355 United States standard miles. At the typical cruise speed of 567 miles per hour, to cover 8,355 miles would take 14.74 hours, or 884 minutes. With 57,285 gallons of fuel, the consumption would average 64.8 gallons per minute. During the first 10,000 feet of climb, the climb rate can be 1,800 to 2,500 feet per minute. At lower altitudes, the engines can produce more power because there is more oxygen in the air. So let's use 2,500 feet per minute for the first 5,000 feet. On takeoffs and landings, how do you make sure that you do not spray chemtrails? Simple. Install a small fuel tank to hold fuel that is not laced with aluminum. They could switch over to the main fuel tank at 5,000 feet. It would take 2 minutes to get to 5,000 feet, so at 64.8 gallons per minute, 130 gallons would be consumed. Upon descent for landing, the engines are throttled back to idle speed and the plane glides, just like the space shuttle. So, on the descent from 5,000 feet, there would be almost no fuel consumed. Let's apply a reserve capacity to the 130-gallon auxiliary tank and make it 202 gallons. With 7.48 gallons to a cubic foot, you would only need an auxiliary fuel tank with a 27 cubic foot capacity. That could be either 3 feet by 3 feet by 3 feet or 2 feet by 2 feet by 6.75 feet. The cargo capacity on a 747-400 is 5,332 to 6,025 cubic feet, apparently depending on whether it is configured in a 524 or a 416 passenger configuration. So fitting a 27 cubic foot tank into the cargo area would not be a problem at all.